Hey, welcome to our explainer. Today, we're going to dive into the secret world of software testing. And no, it's not just about randomly clicking buttons and hoping something breaks. It's actually a really creative discipline, a systematic way to hunt for bugs as efficiently as possible. We're going to explore the smart techniques that professional testers use to break software so that we can ultimately build it better. Let's get into it. Okay, so to get us started, let me ask you something. Imagine you're testing a pretty simple feature, a little box on a screen where you can type in a number of copies to print, anywhere from 1 to 99. Now, to be absolutely positively sure it works perfectly, how many tests do you think you need to run? Just take a second. You got a number in your head? So if your first thought was, well, I'll just test every single number, 1, 2, 3, all the way up to 99, you're definitely on the right track. But hang on, what about numbers outside that range? What about 0 or 100? What about decimals? Or what if someone types in a hello? Or just a bunch of random symbols? See, that impulse to test every single possible thing is what we call exhaustive testing. It's this idea that to be 100% sure, you have to test every combination of inputs and conditions. And the number of tests you'd actually need to cover all of that, well, it's basically infinite. It's just not practical. This is the fundamental challenge, the big puzzle of all software testing. We can't test everything because we just don't have the time, the money, or the resources. It's an impossible goal. So that brings us to the real million-dollar question. If we can't test everything, how do we test effectively? Well, the goal shifts. It's not about running more tests. It's about running the right tests, the ones that have the highest chance of finding a problem. And this is where test design techniques come into play. They're like a framework that helps us choose our tests wisely. All right, so to really start thinking like a tester, we're going to look at software through 3 different lenses. Each one gives us a totally unique perspective for hunting down bugs. We've got specification-based, structure-based, and experience-based testing. First up is specification-based, but you'll almost always hear it called black box testing. Think of it like this. The software is a sealed box. We have no idea how it works on the inside, and honestly, we don't care. All that matters is if we give it a certain input, we get the correct output, based on the requirements. It's just like using a vending machine. You put your money in, you press the button for a soda, and you expect a soda to pop out. Simple as that. Next, we have structure-based, or white box testing. And this is the complete opposite. Now we get to open up the box and look inside. We have the blueprints, the actual source code. With this lens, we can design tests to make sure that every little internal path, every logical decision, every single line of code gets used correctly. We're checking not just that it does the right thing, but that it does it the right way. And finally, there's experience-based testing. This is all about the human element. This is where a tester's own knowledge, their intuition, and their gut feelings come into play. They use their past experience from working on similar apps to kind of guess where the bugs are most likely to be hiding. It's less of a formal process and much more of a creative, targeted bug hunt. Okay, let's put on our black box glasses for a minute. When we can't test every single value, we use 2 really powerful techniques to help us choose the best ones: equivalence partitioning and boundary value analysis. Okay, so this is exactly how we solve our 1 to 99 copies problem. The technique is called equivalence partitioning. What we do is we divide all the possible inputs into groups or partitions, where we basically assume the software is going to treat every value in that group the exact same way. So here, we've got 3 groups: one for invalid numbers less than 1, like 0, one for all the valid numbers between 1 and 99, like 50, and one for invalid numbers over 99, like 100. The idea is simple. If the number 50 works, we're going to assume that 51 and 52 will work too. So we only need to test one value from each group. But just testing one value from the middle of a group isn't quite enough, because as it turns out, a huge number of bugs love to hide right at the edges, the boundaries between these groups. This is where logic can get really tricky, and you get those classic off by 1 errors. So naturally, we have a technique just for that. And this is called boundary value analysis. It's a game changer. We specifically test the values right on the edge and just next to the edge of our partitions. So for our example, we test 0 and 1, that's the lower boundary, and we test 99 and 100, that's the upper boundary. Just these 4 tests, plus maybe one from the middle, like 50, gives us incredible confidence. Way more than if we just randomly picked dozens of numbers. So think about that. We went from a nearly infinite number of tests down to about 5 super effective ones. That's smart testing. Now let's switch lenses. Let's peek inside the box. With white box testing, our goal isn't just about checking the output. We want to be sure our tests are actually making the code do what it's supposed to do, running through all the different logic paths. And we measure this with something called code coverage. So imagine a super simple piece of code like this, right? It just compares two numbers. We'll call them A and B. If A is bigger than B, then it does something. If not, it just skips that part. This if statement right here, that's a decision point. It creates two possible paths through the code, a true path and a false path. Okay, so let's say we run one test. We'll make A equal to 10 and B equal to 5. The condition A is greater than B is true, so the code runs the then part. And hey, our test passes. Great, but look at this chart. We've only tested the true path. The entire false path, what happens when A is not greater than B, is completely untouched, completely untested. We've only achieved 50% decision coverage. Half the logic has never even been run. And this is a perfect illustration of why coverage is so important. To get to 100% decision coverage, all we need is a second test. This time, let's make A equal to 5 and B equal to 10. Now the condition is false, and our test runs down that other path. See? By designing our tests to specifically cover both outcomes of that decision, we can be way more confident that the logic is solid no matter what kind of data gets thrown at it. So we've got these formal techniques for checking the specifications and the code. But what about the stuff that those systematic methods might miss? Well, let's move to our third and final lens, the absolutely irreplaceable human tester. You know, experience-based techniques like error guessing are really more of an art than a science. It's all about using a tester's intuition, that gut feeling to know where defects are probably hiding. They'll try things like dividing by zero, or uploading a huge file, or trying to pay with an expired credit card. Not because the requirements document said to, but because their experience just screams, hey, this is where systems like this tend to fall apart. So, after all that, which of these lenses is the best one? Black box? White box? Experience? Well, the answer is, it's a trick question. You need all of them. A really effective testing strategy doesn't just pick one. It combines them into a powerful, comprehensive toolkit. And just look at how beautifully they complement each other. Black box testing is amazing at finding places where the software doesn't do what it's supposed to do, like say if a feature is completely missing. But it would never find extra malicious code that wasn't in the spec to begin with. On the other hand, white box testing can find that hidden code, but it has no idea if a required feature was never even built in the first place. You really, really need both perspectives. And that's really the key takeaway here. One technique is great for finding defects at the boundaries. Another is perfect for finding flaws in the logic. And that third, experience-based approach is what finds all the weird, unexpected issues that the systematic methods might never dream of. By combining them, you make sure you're hunting for a whole variety of different kinds of defects. So the next time an app on your phone crashes or a website just gives you some bizarre error, think back to these lenses. Ask yourself, was that a bug in the logic that a white box test could have caught? Was it a boundary that got overlooked? Or was it one of those really strange situations that only a curious, experienced human tester would have even thought to try? Thinking like a tester doesn't just help us build better software. It helps us make sense of the complex digital world that's all around us. Thanks for digging into this with me.